Okay, so welcome to tonight's lesson. So in this lesson, we're still on the first part of statics. That's why I'm still calling it the introduction of statics. So we are going to discuss position vectors in 2 and 3 dimensions. And this is our lecture 5. My name is Hampton. So let's quickly begin. So in case you have any questions as we proceed, as I'm teaching, feel free to ask. Yeah. And then if you have any questions or you want to talk to me, or there's something that you want to tell me, or you want to join the lessons, or maybe there's someone whom you know wants to join the lessons, you can simply just use these same lines on the screen and let them contact me, let them reach me using these same lines, and I'll talk to them. All right, so let's quickly begin. So the first thing that we'll start with is first to define what a position vector is. So a position vector is simply just a vector, or I mean, if we talk about position vectors, these are just vectors that are coming from the same origin. So if you have, let's say, let me use white. Okay, so if you have the origin, let's say O, then you have two vectors. We have vector A, and you also have vector B. As long as they are all coming from the same origin there, you call them position vectors. So if you are to find the vector AB, so the vector AB, we are moving from A going to what? To B. So if we are moving from A to B, it means that we first have to go back to the origin, then from the origin, we go to A. So what this means is that if A is in this direction, we are going to oppose the direction of OA. So this vector will be called OA. So since we are moving from A coming to O for us to go to B, so we're moving from A coming to O, this implies that we're going to oppose the direction of OA. So we are going to have something like this. We're going to have OA in this direction, but of course we're going to add a negative there. And then since this other vector is OB and it's in this direction, so we're not opposing its direction, it's just in the same positive direction, hence we just write positive OB. So this is what we're going to have. So we have AB is equal to negative OA plus OB. So AB can therefore be written as OB minus OA. So this is like the basic principle, or this is like the basis of the position vectors. If you have been given to find the position vector, I mean, if you've been given to find the vector maybe AD coming from AD coming from the origin O, it means that what you're going to do is to say negative OD minus, OD minus OA. This is what it means. So you start with this letter there, then end with that. So if you are moving from A to B, so let's say, for instance, if we have this same vector, let me draw it again here. We have this vector from the origin O, then we have A and B. And then let's say we are calling, this vector AB, this vector AB as the position vector R. So I'm no longer going to be using AB. Instead, I'll be using RAB. So to find RAB, this is just going to be what? RB minus RA. This is what we're going to be using. So this is a very important equation that you need to know. Okay, so let's quickly move on. So this is what I was just talking about. Okay, let me just read through the notes. A position vector R is defined as a fixed vector which locates a point in the space relative to another point. So a position vector R is simply just a it's simply just a fixed vector. So what I mean is that if you have the vectors I was drawing here. Okay, let me do this. I'll draw one. If you have a vector in space, so if we say a position vector R, if this is our position vector R, this is just a fixed vector which locates a point in space relative to another point. So relative to the point O. Okay, so a position vector locates one point in space relative to another point. So I think this was just a repetition. That's the same as that. So this is an example of a position vector. Yeah, so you may have, it's an example of a position vector. You may have a vector. You may have this vector R. Then you've been told to write it in a okay, so you may have this vector that has been given here, which is R. And then you may be told to write it in a Cartesian, using Cartesian coordinates. You just have to get the coordinates that you have there, and then you say R is equal to X, and then X, we know to say it's associated with the I unit vector, or unit vector, and then Y is associated with J, then we have Z, which is associated with what? With K. So this is how you write that. Yeah, so if you want to calculate the position of vector, if you want to write it, or if in case you've been given the values of X, Y, and Z, given this point, okay, let me say, if you want to locate this point in space, you can either first go this way, then go like this, and then you go that way to find that. Remember, if we have a point there, and then we have the origin O there, then you want to find the position vector. Want to find the position vector R. Want to find the position vector R. In other words, we're trying to locate this point here using a fixed vector R. So what you first have to do is you can either first move like this and then go that way to locate this point there. Or if you want, you can go this way and like that. You still get the same answer. So this is what I mean. So even here, if you want, you can first go this side, then go like that, then you locate that point there. So now this fixed vector, which locates this point in space, is the one that we call the position vector. All right, so let's quickly move on. So sometimes you may not have one vector. You may not have one vector. Sometimes you can also have another vector in 3D like that. Yeah, so, and then they tell you to find the resultant of these two vectors, this one and that one. So you just follow the same things that we learned in the previous lessons that we had. Yeah, so we have an example on that. I'm going to show you step by step. Okay, so this is what I just talked about. Yeah, so this is like a point. Yeah, so this is just a point. Then the unit vector of this position vector can also be found. So the unit vector of this position vector is simply just found by getting this same position vector R, and then you find the magnitude of this same position vector. So everything that we learned, more especially in the last lesson that we had, are going to apply even on this same portion of this same part of the syllabus. So they are going to apply everything that we've been learning, are going to be applying as we proceed. So one thing about statics and dynamics, which we're going to do next semester, is that whatever that you do is a building block, or it's a stepping stone to the next topic that you are going to have. So anything that we are discussing right now is like the foundation of our next topic. Yeah, so make sure that you are not missing the lessons that we're having. And then apart from that, you'd also make sure that at least if you have missed, you have time to go through the lessons. Okay, so this is what I was talking about. So sometimes you may have two vectors, A and B, and then you have been told to find the resultant position vector. So what this is going to be is that you have this vector going this side, which is vector A. You also have vector B. So to find R, A, B, remember what I said, they are all coming from one origin. So you start with this letter this side, the last letter. That is the way you master it. Start with the last letter. So you just say R, B, then you say minus R, A. So we know that RA has the coordinates RA has Cartesian coordinates as XA. We have XAI plus X AJ plus YAJ plus ZA K. So the direction is also, direction also matters of these coordinates that you have, meaning the signs, the symbols in front there, they're also important. Yeah, now, and then if they ask you to find the direction of the position vector or resultant position vector, you simply just find the unit vector. After finding the unit vector, which is R over the magnitude of R. After finding the unit vector, then you divide the whole vector, the whole what's this resultant vector, you divide it by what? By the magnitude. To find the position vector, which is the unit vector of the position vector that you found. You need to just get the vector that you've gotten there and then divide it by the magnitude of this same vector that you've gotten. So we know to say the magnitude of any vector, the magnitude of vector RAB is simply just going to be given by, let me use white here. So saying we know that the magnitude, the same things we learned, the magnitude of this vector will be given by the square root of whatever that you are going to get as the resultant vector. So yeah, whatever that you're going to get is what you're going to put there. And then to find the unit vector, you simply just have to find the unit vector, you simply just have to divide the vector that you found, the resultant vector, by its magnitude. Then once you do that, you can now apply the cosine, the direction cosine angles. So we know to say cos alpha is equal to, so you can get what you've gotten there in the X. Let me do this one. Well, let me just display what I'm trying to talk about. So the resultant vector R, this is what I was talking about. The resultant vector R is gotten by subtracting RA from RB. Yeah. And then these are the position vectors for RB and RA. So after doing the subtractions there, you have to pair the like terms, you pair this and that, pair this and that, pair that and that. Then you come up with an equation which will look like this. Okay. So let's quickly move on. Okay, so let's take a look at these. Let's take a look at these examples that I've put in the slide. So this is our first example that we're going to have. Then I think we have 3 more, if not 2 more examples. Okay, so it says an elastic rubber band is attached to a point, to the point, to points A and B as shown in the figure. Determine its length and its direction measured from A towards B. So to find its length is simply just the magnitude of the resultant vector. So the length of this rubber band is simply equivalent to the what? To the magnitude of RB. And then the other thing is the direction. So the direction measured from A towards B. So the direction is simply just found by finding the cosine direction angles or direction cosine angles. So once you find the direction cosine angles, those are the ones that you're going to get as the direction of the rubber band. So let us quickly see how we can find that. So how do we get the magnitude or the length of this rubber band? So the rubber band is, we know that it's from A to what? To B. So we have, to find the position vector of this, we're going to say the position vector will be RAB. But of course, if we say we are moving from A to what? To B, meaning we'll have to move from where? We'll have to move, okay, so this one is in 3D, so we expect to have I, J, and K. So this means that we have to move like this. We can move from there, then we can move from there, and then we go like this. Then from there, we move like that. And then I think, which one is a shortcut? Which one is a shortcut for us to, okay, then we go like that. Yeah, so, okay, let's do it this way, not to have done it. So we can move like this. We go first like that. Then after reaching that height, then we move along along the X, then we move like that. So this is how it's going to be. So the distance from here to this point is what is going to be found by adding these 3 here and the other 3 there. So when you add these 2 3s, you're going to get the distance from this point to that point. Okay, or first let's start by identifying the X point. Okay, so we start, we can start first in the X. So to find the resultant AB, this is going to be, so I'm going to open the brackets. So in the X, we're moving from this point to what? To what point? So I'm moving like from this point to which point? To this point where it's turning. So from that point to that point, we know that from there to there, we have what? 1. So we have this one, and then from there to there, we have 2. But remember, the positive x-axis is in this direction. So this other direction represents the negative x-axis. So meaning moving from this point to that point, it means that we have moved -1 units. And then from that point to that point means that we've moved how many units? -2 units. And then we close, then we have I. Then we move on to the Y. So in the Y, we are just moving from that point to that point. So this distance from there to there, I'm sure it has been given somewhere. So the distance from there to there has been given to be what? To be 2. So we are moving 2 units in the Y. So we are moving 2 units in the Y. So we have 2J. And then let us see what we are going to, how long we are going to move in the what? In the Z-axis. So in the Z-axis, we're also moving in the positive direction of the Z-axis. So it's not negative, it's positive because we're going up. So going up, we have this distance from there to there, which is 3, and then another distance from there to there, which is another 3. So we have a positive 6. So we have 3 plus 3. Then we have K there. Then RAB will therefore be equal to, so this part here will give us what? Negative 3I. Then we have 2J. And then we also have this part, which is 6K. So this is the resultant vector A, B. Yeah, so this is the resultant vector AB. So now to find the magnitude of this vector, you can easily just find the square root, the square root of all this. So to find the magnitude of this, I'm going to say RAB in absolute value symbols is given by negative 3. It's given by negative 3 squared. Then we have plus 2 squared plus 6 squared. So we're going to have something like, this will be a 9 plus 4 plus 36. So 36 plus 9 will give us 45 plus 4. This will give us 49. So the square root of 49 gives us what? 7. So 7 units is the magnitude of RAB. So the length of this rubber band is 7 units. So we're using meters, so we can say 7 meters. So the length of this rubber band is 7 meters. So now the question goes on to say, we have to find the direction measured from what? From A towards B. So to find this direction, we have to find the unit vector in the direction of RB. So this is the position vector of AB. So now we just have to find the unit vector in the direction of what? Of RB. So the unit vector in the direction of RB is found by, this will be equal to the whole vector RAB over the magnitude of RAB. So the position, the unit vector will therefore be equal to, so we have negative 3 over 7I plus 2 over 7J. So we just divide everything by 7. And we also have 6 over 7K. So once you do the division, you can now just find the cosine angle, the direction cosines of whatever that you found there. So the first direction cosine of alpha, or the first direction cosine, which is cos alpha, is going to be taken from there. So we have negative 3 over 7. And then to find alpha, you're going to have alpha is equal to what? The cos inverse of this part. So we have the cos inverse of that. And then to find the other angle, so let me first write this. To find the other angle, you say cos beta, which will be equal to 2 over 7. You just get what is there. So to find beta, we just say cos inverse of 2 over 7. And then the other one, to find the value of gamma, we say cos gamma is equal to 6 over 7. And then gamma will therefore be equal to the cos inverse of 6 over 7. So this is how you find the direction measured from A towards B. All right, so we quickly move on. Okay. So let me just show you what I was solving. So this is exactly what we found. And then that is the direction, this is the magnitude of the magnitude or the length of the rubber band. So it's written in terms of the position vector R. Remember I said the position vector is simply just a vector, a fixed vector that locates a point in space. So this is what I was just trying to show you. And then from there, you find the direction cosines. And these are the directions that are showing us how this rubber band is oriented in the plane. Right, so let's move on. What if you have a force that has been directed along a certain line whose position vector can be found? How do you do the calculations? So the same things that I've just explained, the same things that I'm just from explaining is exactly what you're supposed to do. So after doing everything, after finding the unit vector in the direction of R, you find the unit vector in the direction of R. After finding the unit vector in the direction of R, you just need to multiply the force that you've been given by the unit vector. So when you multiply the force times the unit vector, it means that you have found the force. You have found the force in the direction of. We have found the vector force or the force vector that is directed along that given line with this position vector R. Okay, let's take a look at some examples. So this is what I'm just trying to explain. So you first find the unit vector in the direction of along that same given line, and then you multiply it by the force. Then this is going to be your result. All right, so let's quickly look at this example so that you can have time to do the exercises. And then there are also those people that submitted the exercises yesterday. I was a bit busy, so I couldn't mark. Yeah, so I'm going to mark them tonight and I'll forward them to you. And then for those that have not yet done the exercises, make sure that you do them so that you at least test your understanding. And then even the exercise that I've put in this one, in this slide, they are very simple. They are very simple questions that you can do even just within 30 minutes. All right, so let's quickly solve this question. So the question says, okay, let me change the color. The question says, the man shown in the figure pulls the cord with a force of 70 pounds. Represent this force acting on the support as a Cartesian vector and determine its direction. So to express the force that is in this cord, you simply just have to find the unit vector in the direction of this same cord. And to find that, the first thing that you need to find is the value of R, which is just the position vector in the direction of AB. So the position vector in the direction AB is found by RB minus RA. That is how we find the position vector in the direction of AB. So in this case, we are dealing with 3 dimensions. So what you do to find the position vector in the direction of AB, you take the values of RA and RB in all the 3 axes. So when we take in the X, so in the X, I'm going to open the brackets. So in the X, how are we going to move in the X? So to reach this point in the X, we just move along the positive X, meaning we're just going to move from where? Where is the origin, by the way? The origin, okay. The origin is there. So in the X, we're just going to move, so in the X, we're just going to move this distance from there to there, because this is the X. So we are going to have our 12 there. So we're going to have our 12 there. And then in the y, so we have I, and then in the y, we are going to move the distance from 30 to what, to, I mean, the distance from there to there is 30. So you just subtract 30 minus 6, you're getting 24. So you're just going to have 24 j. So I'm just trying to find the position vector. Or I think let's do this. Let's let me just end the meeting and quickly join using the same link so that we just start. I don't want this meeting to end at a point where we don't expect it to end. Yeah, so it's I mean, it disturbs in most cases. So let me end the meeting, and then you join using this same link, the same link that is in the group. Just click on that so that we proceed with the question.